Hello. Today I will be presenting on absorption spectroscopy. Shop. Anyhow, today I'll be presenting on absorption spectroscopy and its uses in the assessment of the electronic structure of cyanide dyes, with comparisons to molecular models and computational models. There we are. The research goals for this experiment was to determine how absorbance changes as a function of the conjugation chain length in these cyanide dyes, and to assess the accuracy of different molecular models in predicting the HOMO-LUMO gaps of these dyes. In particular, we looked at the particle in the box method, the Huckel molecular orbital model, Hartree-Fock approximation, and neglect of diatomic differential overlap models. And why do we even care, though, if these models are accurate? Well, we care because they're commonly used in physical chemistry and they're essential to computational chemistry. So we actually do care if they're accurate, and in future applications if they do a good job. So what do we think is actually going to happen here? So the hypotheses that I present are that the wavelength of maximum absorption will increase with increasing length of the conjugated hydrocarbon chain between the cyanide moieties. Essentially, as the length of the system increases, the energy gap will decrease at a faster rate compared to the increasing in the number of electrons that are dealing. The other hypothesis I present is that the Hartree-Fock, or rather the MNDO method and its improvements in Segrest, will most accurately predict the HOMO-LUMO gaps of dyes. These models are the most refined and expanded. For example, unlike the particle in the box or the Huckel model, this model accounts for intermolecular interactions which can impact the HOMO-LUMO gap. Next, we really want to talk about what's happening in this experiment. So in this experiment, we used absorption spectroscopy. Essentially, we had a UV-vis source that produced light that shined through our sample, essentially going through a biconvex focal lens, bouncing off of a mirror, and our sample cuvette was placed at the focal point, and then the light was bounced back through another bifocal lens or biconvex focal lens and directed at the detector. Essentially, we use methanol as a blank and ran it before each run, and then adding a few drops of the dye into the methanol and getting a spectra of the absorbance. So essentially how absorption spectroscopy works is that our light source, which is a UV LED and incandescent bulb, produces light, which travels through the cuvette with the dye. The dye absorbs some of the energy, and so the light that passes through the dye, when it's not absorbed, reaches the detector, which was an Ocean Optics USB 4000 CCD detector, runs through computer and some programming, and spits out a spectrum where we can analyze this for the wavelength of maximum absorption. This resulted in our results, in which we were able to get a spectrum for each dye absorbing at maximum wavelength of absorbance from 424 to 757.9 nanometers. So as we predicted, the wavelength does increase as the length of the conjugated chain increases. Now, how do these models actually compare to the theoretical models that we care about testing here? So firstly is a particle in the box model, in which it basically models an electron in a infinitely deep potential well, in which the energy levels follow this equation here, where n is the number corresponding to the energy level. H is Planck's constant, mass is the mass of an electron, and the length is the length of the molecule or the conjugated system in this case. And we found the HOMO-LUMO gap, and where N1 is the n level of the HOMO, so it's the number of pi electrons divided by 2, and then N2 is N1 plus 1, and the length was determined from bond lengths. So this was able to be used to predict the wavelengths, and ultimately there were percent errors from around 1 to 20%. So it's pretty good for die 3 and 4, but not very good at predicting die 1 and 2. Now, the next model that we used was the Huckel molecular orbital model. And so that is where it's essentially a specific case of a molecular orbital model, using an n by n secular determinant to find the energy of molecular orbitals, essentially converting Schrödinger equation into a matrix which can be solved for the energy. But the Huckel approximation makes this easier by saying that this term here is equal to 0, or the Hij terms are ignored unless you're talking about adjacent atoms. For adjacent atoms is equal to k beta. It's simply equal to beta for carbon, but the k accounts for is a constant that accounts for atoms that are different than carbon, like nitrogen or sulfur. For nitrogen, it's 0.8. And then this term for orbitals on the same atom is equal to alpha plus h beta, where h is equal to 0 for carbon, so it's equal to simply, the whole term is equal to simply alpha, but is equal to 1.5 for nitrogen, and this is something that we have to consider in our calculations of these cyanide dyes that have nitrogen. But this is an example matrix that we can construct, so it's essentially turning this really complicated determinant into this matrix here where x is equal to alpha minus e over beta. So essentially we use this same sort of formula but adjusting for the nitrogens to do Huckel matrices in Mathematica, and spit out the results in a term of where x can be solved for, finding these values of x. So x times beta is the energy level, where beta is a unit of energy. So for each dye, we essentially constructed these energy diagrams, filling them up with the number of electrons. So for the first dye, there was 6 electrons, 6 pi electrons. So you filled the first 3 energy levels. And the energy difference between here is delta coefficient. Delta coefficient times beta is equal to the energy gap, where beta, the value of beta used here is a literature value of beta. And thus we are able to convert this value of beta into wavelength with this equation here. We are able to convert delta coefficient into energy from this equation here, and then convert energy to wavelength from this equation here, and get these values of wavelength to compare our HMO predicted wavelengths to the experimental wavelengths, and get percent error. The percent errors here are smaller than that of particle in the box in general, but are better for these shorter dyes than the longer ones. Now, the last thing that we did was to use molecular modeling, semi-empirical methods to calculate the energy gaps. And these methods are all based on the Hartree-Fock approximation and the neglect of diatomic differential overlap and DDO models. So the Hartree-Fock approximation is essentially taking, so if we look here, we need to solve for the Schrödinger equation to get energy. The Schrödinger equation has this electrostatic potential energy term, which is really honestly impossible to kind of solve for a multi-electron system because you get a whole bunch of multi-electron integrals, which are really hard to solve for. So what the Hartree-Fock approximation does is essentially replaces this term with an approximation where electrons interact with an average electrostatic potential field, and thus we are able to make those calculations. However, Hartree-Fock is a nonlinear integral differential equation, thus is very difficult to solve analytically, so instead we use computational methods in which molecular modeling and SciGRESS is used using these different molecular modeling packages, MNDO, AM1, RM1, and PM3. AM1, RM1, and PM3 are all essentially improvements on MDO. MNDO is based on a limited data set behind its parameters, so it's essentially the most limited in its applications. AM1 alleviates some of the problems with short rate interactions that were in MNDO. So this is like the first sort of improvement on NMDO. And it also more accurately described hydrogen bonding than MNDO, which tends to have a very poor description of hydrogen bonding. PM3 is a reparameterization of AM1 that uses less Gaussian functions, and RM1 is also a reparameterization of AM1 that uses a more complete training set of training data. This more complete set of training data would suggest that RM1 would likely be the best at describing sets of molecules with heteroatoms, so a heteroatomic molecule. And these are our results. Whatever one wins, some conclusions. Thank you. Thank you for your time. I hope you enjoyed this. Have a lovely rest of your day.